According to legend, a king was so delighted with the game of chess that he asked the man who invented the game what he wanted as payment for such a wonderful game. The man replied, 1 grain of rice on the first square, 2 grains of rice on the second square, 4 grains of rice on the third, 8 on the fourth, etc., until every square on the chessboard is filled. Now there are 64 squares on a chessboard, so I think I would like an efficient way to add this up. I did notice that this is a geometric sequence. 1 plus 2 plus 4 plus 8. We're multiplying by 2 each time. So how can I efficiently add up all of those 64 terms? Well, let's go down here where it says deriving the formula for the sum of a geometric series. Any series can be written as the sum of the terms from 1 to n. Sum s sub n, a sub 1 plus a sub 2, etc. Now recall that if we're in a geometric sequence, that a sub n is equal to the first term, a sub 1, times r to the n minus 1. So if I wanted to fill in what these terms would look like specifically for a geometric sequence, they would look like this. S sub n is equal to a sub 1 plus a sub 1 times r to the first, plus a sub 1 times r to the second, plus a sub 1 times r to the third, plus, and then if this is a to the n minus 1, the term before that would be a sub n minus 2. In other words, to get to term n minus 1, I would need to multiply by r n minus 2 times. So this would be a sub 1 times r to the n minus 2. And then to get to a sub n, it would just be a sub 1 times r to the n minus 1. So specifically for a geometric sequence, this would be what it looks like to add up the terms from 1 to n. Now, there isn't any really efficient way to write this in a compact way without doing a little bit of algebraic manipulation. So I'm going to do something here. I'm going to, right below this, I'm going to write the same sequence, only I'm going to multiply both sides of the sequence by r. So this would be a sub 1r now. This would be a sub 1r squared, a sub 1r cubed, a sub 1r to the fourth, and so on. This is going to be a sub 1 times r to the n minus 2 times r to the first. So if I have r to the n minus 2 times r to the first, and I add n minus 2 plus 1, I'm going to get n minus 1. And a sub 1 times r to the n minus 1 times r is just going to give me r to the n minus 1 plus 1, so this would be r to the n. Okay, so now what's going to help me to reduce these numbers of terms is to notice that I have a lot of duplicate terms here between the first row and the second row. So if I subtract the second row from the first row, a lot of these terms will subtract out. So I'm subtracting every term in the second equation from the first equation. So these terms subtract, these terms subtract, these terms subtract, these terms subtract. And the a sub 1 r to the fourth is going to subtract from whatever's up here next to the next term here. And this one's going to subtract from the with the previous one down here. So everything's going to end up subtracting out except the very first term and the very last term. So this simplifies to, on the left-hand side, s sub n minus r times s sub n equals a sub 1 from the first row here minus a sub 1 r to the n. This is going to give me a really nice compact formula for adding up the first n terms of a geometric sequence. If I factor out an s sub n on the left-hand side of the equation, and I factor out an a sub 1 on the right-hand side of the equation, recall that then this would be s sub n times 1 and s sub n times r, so that would multiply back to give me what I had originally, and divide both sides by 1 minus r, I end up with a compact equation now. S sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. Now this formula does not have any intuitive sense to it, like the sum of an arithmetic sequence where we added the first term and the last term and half the number of terms. This is something you just have to use, okay? And it works. It's based on things we know, but it's not something that makes intuitive sense just in and of itself. So I'm going to try to position this so I can see my sum formula down here, and I'm going to apply this now to this problem with the chessboard. So in this sequence, here's my a sub 1, r is 2, and this is n because I'm adding up 64 terms. So I'm going to say s sub 64 is equal to 1 times 1 minus 2 to the 64th power all over 1 minus 2. Now if I put this in my calculator and calculate this, I end up getting 1.845 times 10 to the 19th grains of rice. That is an exceptionally large number. I'm going to show you this picture here. This is a little screenshot of a little bowl of rice that I got from my house. I had a 2-pound bag of rice. So I'm going to write this down. A 2-pound bag. I took 1 tablespoon from that bag. 1 tablespoon of rice, and I counted every grain in that tablespoon. 1 tablespoon had 650 grains of rice. I needed to know how many grains of rice then were in the whole bag. So what I had to do then was figure out how many tablespoons were in. So first of all, I started with cups. There were 4 3/4 cups of rice in the bag. And I also know from cooking that there are 16 tablespoons in 1 cup. Because I was curious. I wanted to know about this amount of rice. Is it enough to fill up my whole classroom? Would that be that much rice? Would it just be a whole bunch of large bags? You know, what kind of size would this rice take up? How much would it weigh? How much space would it take up? So that would be a good question to see if you could answer. How much space would it take up? Like how much volume would it take up? How much would it weigh? Okay, so it's a 2-pound bag, so you could look at how much space it takes up by looking at you know, the cup, how many cups it would fill up. You could also look up how much weight it would be. So at the end of the video, I'll give you what I found out. But if you, I'll do kind of a spoiler alert. So if you don't want to know and you want to figure it out for yourself, you can do that. So I'm going to leave that for right now. I want to apply this rule to a couple more example problems because there are some times when the computation of this, you can make some careless mistakes that I want you to avoid. So I have 2 more geometric sequences. They're identical except one's getting bigger and one's getting smaller. In this one, we're multiplying by -4 each time. So in this case, we have r equals -4. And I want to find the sum of the first 12 terms. So I'm going to say s sub 12 is equal to 1.5 times 1 minus -4 to the 12th power over 1 minus -4. Now, one mistake that a lot of students make is they look at this and they see a minus a negative and they say, oh, that's just 1 plus 4 to the 12th. But it is not, and I'm going to show you why. If you do 1 minus a -4 to the 12th written like this, you get a large negative number. If you do 1 plus 4 to the 12th, you get a large positive number. So why are they different? It's because of the order of operations. You have to do the exponent before you do the subtraction. And when you do -4 raised to an even power, it becomes a positive number. And then you subtract the positive, this large positive number from 1. Here you're making the subtraction positive before you've actually applied the exponent, so you end up with the wrong answer. So what is actually the final answer for this? If you do the first term, 1.5, and then times in parentheses, and I'm just going to go up and grab the correct way of writing this, in parentheses, and then down here 1 minus a negative 4, and I'm going to do a control enter to get, this is the correct answer. Okay, negative 5033.1645. So I am going to copy this into my file here so we can show that there's a correct way and a not correct way to do this. So you might, if this is something you're afraid you might do by mistake, you might want to write down that there is the correct way and the not correct. So this is correct and this is not correct. Okay, so you want to go ahead and leave the parentheses and type it in exactly as written. So this turns out to be a negative number, negative 5033164.5. If you were to do it using this method, you would have ended up with a different answer. Okay, so different answer. You'd end up with a large positive number instead of a large negative number. Now notice in the denominator though, 1 minus a negative 4 does turn out to be 1 plus 4, but it doesn't in the numerator. Okay, now the other one is the same sequence, only the other direction. So instead of multiplying by negative 4, I'm actually dividing by negative 4 or multiplying by a negative 1/4. So r is equal to negative 1/4 or negative 0.25. And I want to find s sub 12 here. So s sub 12 is equal to 96 times 1 minus negative 0.25 to the 12th power all over 1 minus negative 0.25. So if we do this on the calculator, okay, so I type this all in exactly as written with correct parentheses. Okay, we get 76.7999. Now I want to point out something, just kind of some common sense things to think about. Number one, on the first example, notice that as we go from term to term, we're alternating positive, negative, positive, negative. Notice each term gets bigger than the one before and also alternates signs. So if I had added the first 2 terms, I would have ended up with a negative number. If I add the first 3 terms, I would have ended up with a positive number. Well, if I add the first 4 terms, I would end up with a negative number because whatever I end on, whether it's negative or positive, that number is bigger than all the things that have come before it. It's even bigger than all the things that have come before it added together. So if I were going to the 12th term and I got a positive number, that wouldn't make sense because my 12th term is going to be a negative number that is larger than all of the numbers that came before it. So you need to think about common sense when you look at your answer to see if it's reasonable. Okay, now here, when I add a term, when I go from negative 96 to negative 20 and then subtract 24, the number is still positive. And when I add 6, it's still positive. And when I subtract 1.5, it's still positive. 96 is the very biggest number and everything else is getting smaller and smaller. So I'm never going to get a negative number for any of the sums here. It will always be positive. Also, if I do 96 minus 24, that is 72. And then plus 6 would be 78, minus 1.5 is 76.5. Notice this answer is really very close to 76.5. Even though I've added 8 more terms, it's still pretty close. Well, why is that? Well, let's think what happens when I'm adding these other terms. So if I start out with 96 as my first term, and then I multiply this by negative 0.25, and then I keep multiplying. Oh, so that should be negative 0.25. Let me delete this and do that again. Okay, so times negative 0.25. There we go. And then I push enter. Then I enter. That would be 6. Then I get the negative 1.15. So let's see what happens next. So this is term number 5, term number 6, term number 7, term number 8, term number 9, term number 10, term number 11, term number 12. Okay, all right, so this number is, I thought that might be actually multiply it out, but it's not. This is negative 2.288 times 10 to the negative 5. In other words, 0.00002288. So as we are adding more and more terms, we're adding terms that are getting closer and closer to 0, so they're not making a whole lot of difference in the overall sum. So we're going to look at sequences like this. This particular type of sequence has something special about it that we're going to deal with in our next video. Okay, spoiler alert. Let me show you let me show you what happens when we figure out all those grains of rice. So using those measurements that I gave you, I found that a tablespoon had 650 grains. In a 2-pound bag, which was 4 3/4 cups, it had 76 tablespoons, 16 tablespoons per cup, so 49,400 grains of rice in a 2-pound bag. Now remember, I'm dealing with 1.845 times 10 to the 19th grains. That's a lot of rice, okay? That's a lot of rice. That is this much rice, okay? So I needed to kind of, condense this down. So I found out that 1 U.S. ton was 2,000 pounds. Well, if I know that a 2-pound bag has 49,400 grains, then 2,000 pounds has 49,400,000 grains of rice. And I thought, well, that's still not nearly as big as this number. So I wanted to think, if that's a ton, how many tons of rice are there in the world? Like, how big is a ton of rice? So I found some information about that the world rice production in 2011-2012 was about 2.614 times 10 to the 16th grains of rice, which I got from a metric ton. It was in metric tons, 480.1 million metric tons. It's spelled differently. So I had to convert from a U.S. ton to a metric ton, which I found out how to do online. So a metric ton has 54,454,188 grains. So that means 480.1 million tons is this many grains of rice. So basically what the king paid the man who invented the game of chess was 705 times the world production of rice in 2011. Because if you take the amount he was paid divided by the actual amount of rice produced in 2012. So this is an enormously huge amount of rice. No way the king could pay up. It's impossible. It was more than the rice produced in the whole world. So just in case you were wondering, I thought that was pretty cool.